Thank you very much, Josh, for the invitation and also for the introduction. And thank you everyone for coming to this session. Today I'm going to talk about a very recent work on bidding in uniform price auction for value maximizing buying. And it's also joined for my first year PhD student, Saurabh Sahul, who's actually the main brain behind it. Okay, so let's start with an introduction about uniform price auction. This auction is widely used in practice. It's used in emission pyramid auction, which is also known as carbon market. It's used in treasury auctions. It's used in energy markets. So how does it work? As many of you know, so in this auction, we have k-identical units of a single item. For example, in carbon market setting, the items that we are auctioning off is the carbon license, which give polluters permission to emit 1 ton of CO2 in air. So then on the other side, we have buyers that they have demand for multiple units. And then after the bid gets submitted, the case highest bid would be declared as a clear. And then what is interesting about this auction is that everyone would end up paying the same price for the unit that they ended. And that's where the name is coming. So just let me give you an example to make the auction format more clear. Suppose that I have two bidders, Alice and Bob, and then I have 5 units to add. Now let's say Alice submits this vector 55333, meaning that for the first unit that she's interested in, she submits a bid of 5. For the second one, submit a bid of 5, etc. And then on the competing bid coming from Bob, it would be like 4422. Then after that, the bid gets sorted. And then since I have as an auctioneer 5 units, the top 5 bids get allocated. And then the fifth highest bid, which is 3 in that case, would be the clear. So you will see that Alice gets 3 units, Bob gets 2 units, and the clearance price, as I said, would be $3. And then Alice and Bob pays 3 times 3, which is $9, and then Bob pays 2 times 3, $6. Is that clear how it works? Awesome. Now, you may wonder why uniform price auction is being used in practice. So there are various reasons. One reason is that it has equal price for everyone, right? In some cases, it's actually illegal to discriminate, to have discriminatory prices for identical items. And then when you have a single pricing, it's good for fairness. There are also other reasons why this uniform price auction is quite common in practice, and that includes reduction in market manipulation. Although I have some recent ones that actually argue against that, but let's believe that this all type of auction actually reduce market manipulation. And the third thing would be like, some people believe that in this auction format, as a bidder, your work is very easy. You end up like go with the rules. But in fact, when it comes to this last statement, there are argue against it, and there are also argue to support that. From the theoretical perspective, there are a lot of like papers that argue that in this auction, buyers do demand reduction, meaning that they are not going to be truthful. The bid they submit is going to be less than their average. On the other hand, we have these empirical studies that people try to actually argue that this auction promotes truthful bidding. And in fact, especially when you have a large number of bidders, actually, they're going to argue that people are going to be used. So in this one, we want to understand what's going on, like why there is this conflict between theory and empirical studies. And we believe that one of the reasons that these two these like type of studies don't agree with one another is related to the behavioral model that people consider for the buyers in these auctions. In particular, as many of you know, in the classical mechanism design, people assume that buyers are quasi-linear maximizers. They maximize the total value minus total payment. And if that's the objective they are looking for, it's easy to come up with an example where bidders try to do demand reduction. They try to actually like be non-truthful and in order to reduce their clearance. So instead of considering this classical model, we are going to go with value maximizer setting, where in the value maximizer setting, buyers maximize their total value subject to some financial constraints. It could be budget constraint, it could be like a soft budget constraint, it could be like a hard budget constraint, it could be like a soft financial constraint, like return on. And this type of modeling is quite common in consumer choice modeling, when people such as an agent trying to maximize their value subject to budget constraint. Also, for many, this will be our audience for auto bidding in online ad market, as many of you know, in online ad market. After the introduction of the auto bidding and auto bidders, we know that these auto bidders try to maximize value on behalf of advertisers and on that. And I also have myself have worked on that. So in any case, so we are instead of looking at quasi-linear maximizer, we are going to look at value maximizer and try to see that if by looking at this value maximizer, we can try to come up with this kind of like conflicting theory for uniform price function. And in particular, we try to answer that if value maximizer bid truthfully in uniform price function. Try to understand their bidding behavior and try to understand if by looking at this type of behavior, we can try to kind of bridge the gap between theoretical and empirical. Any questions so far about the research question? Sure. So to answer this research question, I'm going to present a simple model. And then, okay, so here's a model. So I'm going to look at the problem from a perspective of a single bidder. Just think about Alice in the example. Now, Alice has the evaluation vector V1 to Vk, where V1 is going to be greater than V2 up to like Vk. The way to think about this Vi would be the marginal value of allocating unit I to Alice. And okay, so for example, here, if Alice gets 1 unit, she gets the value of V1. If she gets 2 units, her total value would be V1 plus V2. If she gets 3 units, her total value would be V1 plus V2 plus V2. Okay. And now, just a little bit of notation, because it comes handy in the rest of the talk. So I'm going to define Wj as the average marginal value for the first J, meaning that W1 would be V1, W2 would be V1 plus V2 divided by 2. Okay. Now let's try to understand what bidding format our bidder or Alice is gonna use. And for the bidding format, I'm gonna go with M uniform bidding. How does it work? So the bidder is gonna submit M pairs of bid value and quantity, rather than submitting 1 bid value for every unit she's interested in. So it turns out that like it's going to submit a pair of B1Q1, B2Q2, BMQM, meaning that for the first Q1 units, the bid is going to be B1. For the next Q2 units, it's going to be B2, and then for the last QM units would be B. Why am I considering this? Because it's very common in practice. In a carbon market setting, for example, the number of units to that is being auctioned off and the buyers are interested in the order of millions. So we don't expect buyers to submit a vector with the size million. That's why this type of like bidding format is quite common. And for example, like in European emission trading system, M is the order of average and between 1. Okay, cool. Now let's get to the important part of the modeling. Which is about like value maximizers. For that one, I'm looking at the repeated setting where we are running a uniform price auction over the course of T rounds. And then here I'm using beta minus T to represent the competing bid in round T. And then I'm using capital B for value and capital B for the. Okay, so now this bidder wants to maximize the cumulative value it gets over the T rounds. And this bidder has this return on investment constraint. So note that I have parameter gamma here, where the gamma would be a number greater than or equal to 0. And I'm going to refer to gamma as a target return on investment. Another important aspect when it comes to modeling is that I have a per round return on investment rather than cumulative return on investment constraint. And this is because unlike online ad market, the frequency of these auctions in practice is not huge. So for carbon market, we have few auctions per week. So that's why it's important to have this constraint per round. And also in some cases, there's a chance that this future auction get canceled. So we want to make sure that the bidder manage to get the return that they want for every round rather than waiting to get the return. And the last thing would be I want to make sure that bidders submit M uniform bid, meaning that they're going to submit at most M pairs of bid value. Now, I'm going to say that this bit vector B is feasible if the ROI constraint is satisfied in all domains. Now, here's the important things that I want to argue in the next slide. I want to argue that in the setting I consider, this bidding policy being feasible is not going to be. We need something a bit strong. So let me argue for that. Suppose that I'm looking at the problem again from the Alice's perspective, but I'm looking at the problem in an online setting, meaning that Alice does not know what Bob is going to say. And now suppose that Alice only wants to submit one pair of bid and quantity, and that's her evaluation. And so far in these two rounds, these are the bids that Bob submitted. This is the bid in the first round, this is the bid that Bob submitted. Now, with some effort, and I don't expect you to do the math now, you can figure out that optimal feasible bid, which is the one uniform bid, would be a pair of 6 and 3, meaning that Alice submitted a bid vector of 6, 6, 6. Now, let's say in the next round, Bob ended up submitting this beta minus 3, 7, 5.5, 5.5, 5. But Alice uses the optimal bid that she calculated in the previous two. So then you can see that with that bid, Alice is going to get $15 as her value, but she ends up paying $18, meaning that her ROI is violated in that. But I'm trying to argue that instead of like B being feasible, I want B to be universal. Which means that irrespective of what Bob is submitting, I just want to make sure that Alice's bidding policy satisfies her ROI constraint. And that's what I mean by universal feasible policy. Let me pause here to see if this definition is clear. Okay. Rather than making sure that the bidding policy B is only feasible on the rounds that Alice has already seen so far, I want to make sure that this bidding policy is feasible for all the future rounds and any possible competing bid that is coming from Bob or any other. Seems like a very strong restriction, but then you are going to see it comes handy, and the cost of that would be small. Yes.
This is not adaptive, right? The future bids are not going to be adaptive.
It could be adaptive or non-adaptive. So I'm trying to say that regardless of what competing bid Alice's will face, I just make sure that Alice's ROI constraint that's for any possible company. Yes.
It's the same bid throughout.
No, it can't change. It can't change. It doesn't have to be the same. But
so what does Alice know? Does Alice know the time?
Alice doesn't know anything. Alice doesn't know anything. I just but without knowing anything, Alice still wants to be ROI. It seems very strong, right? So it seems like we are imposing a lot of assumption on the bidding strategy that Alice needs to follow, but you will see that this is not actually very strong. Cool. So based on that, let's go back and revisit our research question. Let's see what we want to do. So the first question was about how do value maximizer be the uniform cross-section. So now I'm just instead of that question, I'm going to have 3 sub-questions. First one would tell in the first one we want to figure out how to characterize the optimal universal feasible bidding policy. The second one would be how good this policy are, right? Am I paying so much cost by enforcing it to be universal feasible? And the third thing is that is it easy actually to learn this policy? And then the second question was about how do value maximizer if value maximizer bidders be usefully. For that one, I'm gonna revisit that and I will say our optimal UF policy is in some sense Now let's get to the first question. Let's try to understand how this optimal universally feasible policies would look. Okay, so to explain that, I'm going to introduce the concept of underbidding and overbidding, which is actually, we'll see, is very well connected to ROI constraint, return on investment constraint that I defined. And this underbidding and overbidding concept allow me to characterize a class of the use cases. Okay, so remember that ROI constraint tells you that total value should be greater than 1 plus gamma times total. I can rewrite this as the average value per unit scaled by 1 plus gamma greater than per unit price. Now you will see that this average value per unit, this WJ that I defined, is started actually showing up. So based on that, this idea of we came up with this idea of underbidding and overbidding. Usually underbidding and overbidding is defined with respect to the valuation curve. Instead of that, given what I have above, so I'm going to define underbidding and overbidding with respect to W. In a sense that if the bid is above W, is below W, I would say it's underbidding. If it is above the W curve, I'm going to call it over. But it's the same concept, right? So instead of like defining it with respect to W, the valuation curve, I'm going to define it with respect to the, which is the average value for the first, for example, J. Okay, now here's our first theorem that says that the class of all non-overbidding bidding policy is the class of real policy. Meaning that as long as Alice does not overbid, she's safe. Just we need to ask Alice not to overbid, and as long as she does that, her ROI constraint is always satisfied, irrespective of what bonds. Non-overbidding is equal to universal. Yes.
Just clarification. So I may have misunderstood. I thought UF was parameterized by gamma.
Yeah, okay. So I'm a little bit okay. So here when I'm saying W, like this is scale W divided by 1 plus gamma. So I'm being a bit
I see.
Thank you for that. Yeah, and also like when I'm saying non-overbidding, meaning that not above W divided by 1. In the picture, like normally right. Okay, cool. So now, but this is good, right? This is simple from Alice's perspective. Don't overbid, you're going to be safe from the in terms of like satisfying ROI constraint, you're going to be universal. But okay, this is great, but then we have from the Alice's perspective, Alice needs to deal with infinitely many number of problems. I made her life a little bit easier, but not so much. So that makes us wonder if there's like a subset of this class of policies that are hard to optimize. But hopefully you are fine. Yes.
I guess why the slope of this W is negative?
Oh, because we have this diminishing marginal value, meaning that V1 is less than is greater than V2, V2 is greater than V3, etc. The value for the value for the first unit is the highest. The value for the second. Okay, so now this makes us it's a subset of this class of policies compared to optimal, and the answer is actually yes. As long as Alice does not overbid or underbid, meaning that Alice actually bids truthfully, so that class of policies is optimal universal reserves. In particular, optimal year policy takes the following form. If you submit this K pair of bid value and quantity, BL should be WQL. QL it would be the number of demanded units in the first L pairs, normalized by 1 plus. Meaning that as long as you are in this W curve normalized by 1 plus gamma, meaning that you are not overbidding or underbidding, you are being truthful. So that's the optimal class. Okay. So let me actually parse this.
How the QIs are defined?
Yeah, good question. So, so let me give you an example to make it more clear. Suppose that Alice decided to go with Q1 of 3, meaning that like for the first pair the quantity is 3, for the second pair the quantity is 4, and for the last pair the quantity is 2. Okay. No, and these are like the values that Alice has, like V1 up to V. Then let me calculate the capital Q, capital Qs. Remember this Qj is the number of like demanded units in the first J pairs. So Q1 would be equal to little Q1 would be 3. Capital Q2 would be Q1 plus Q2 would be 7. And then Q3 would be 3 plus 4 plus 2 would be 9. Is that clear? Okay. So after you calculate these capital Qs, the bidding is very simple. You just need to make sure that you are truthful. So B1 would be W3, which is the average value in the first 3 units, normalized by 1 plus gamma. B2 would be W7, which is the average value in the first 7 units, normalized by 1 plus gamma. And B3 would be W9 divided by 1 plus. So this theorem tells you that as long as you have the value for the Q, you decide about your quantities, the bits would be determined in that way, meaning that the bits are truthful. And note that this class of pulse is actually finite. It's exponentially large, but it's still finite. So what are the main takeaway message of this theorem? The first thing is that the optimal UF policy have this very nice nested structure through this capital Q. Other thing is that the optimal universal feasible policies is a kind of a generalized truthful bidding strategy. In a sense that this class that I define is only depends on the valuation curve. It only depends on gamma, and that's all, right? And the third thing is that to determine the bits, you only need to optimize over the Qs. As long as I have the Qs, I should just follow the truthful bidding strategy, and that's it. Yes.
But the choice of the cues could depend on other.
Yeah, exactly. The choice of the, and then later I'm going to come back and see that how we can learn this the value for it.
But you still regard this as truthful then? In this
Yeah, I think to me it was also quite, yeah. So you may debate that this is not exactly truthful, but I think from the bidder's perspective, if M is equal to 4, and then I'm saying that only looking at this type of truthful bidding strategy, I still personally would like to call it truthful, but I can say that there are arguments against it because the choice of the Q depends on the company.
So the choice of Q is not predetermined in any way, there is no true Q, right? Or there
There's
is.
no true Qs, and then later I'm going to tell you how you can learn Q, the optimal Qs over time. Good question. Any other questions? Okay, awesome. So now let's go back to the research question. How to characterize optimal universal feasible policy and show that it's a nested policy. We wanted to see that if the value maximizer buyers would be truthfully. Yes, they do at least. If you have my point of view, they follow some generalized truthful beliefs. Okay, so now let's go to the other question. How good these universal feasible policies are? Because they give us this simplified bidding strategy, this nested truthful bidding strategy, but at what cost? Am I paying too much for getting this simplicity? What's the cost of enforcing universals? So for that one, we introduced the idea of the price of universal feasibility, which is similar to the notion of price of anarchy or price of flexibility. So the way it works is that we would say first, let's try to see what we are solving from the bidder's perspective. So far, we wanted to make sure that the bidders maximizes her total value given the competing bids. ROI constraints are satisfied, BM is in uniform, and B is universal. This is what we've been looking at, and we say that the optimal solution to this problem, which we call it BMUF, is one of these nested policy that we do. As a benchmark, I'm going to looking at the same optimization problem, but I'm going to remove the restriction that B is universal feasible. I still want the ROI constraint to be satisfied, but I don't want to be universal. And as I said, this is going to be my benchmark when I define the price of universals. So then the price of universal feasibility will be the ratio of BM opt, which is the optimal value by any feasible policy, not the one that is necessarily UF, divided by BMUF, which is the optimal value that the bidder gets by restricting to be universals. So now here's the exciting result that it kind of makes us very happy, because that shows that the price of universal feasibility is upper bounded by 2, and this is the bond, this bond is actually for any value. This one is true for any value of M, and this one is type for any value, for any number.
I have a question. So for the competing bids, B minus I, are they selected adversarially or subject to some prior distribution?
It could be anything. So that's why here, that's a very good question. That's why here, I have maximum over the competing bids. The competing bid could be anything, could be adversarial chosen could be large or small, any value, but still the price of universal feasibility would be upper bounded by 2. Okay, so I think if time permits towards the end, I'm just going to show you how we show this theorem. But for now, I'm just going to walk you through the tight lower bound for the case of M equal to 1, when the bidder wants to submit one pair of bid and quantity. Okay, so there we consider n rounds, and then the number of units would be n plus 1. And then now the value of Alice is almost 1. Is 1 V, where V is like slightly lower than 1. So these are the competing beats that, for example, Bob submitted. For example, in this round 1, you will see that Bob submitted very large beats. C is a number much greater than 1. And only his last bit is just the smallest epsilon. Like all round T equal to 2 is like that, or up to like T equal to N minus 1. The last round, I would call it an easy round. So I have a bunch of like very difficult and competitive rounds where like Bob is submitting very high beats. The last one is the round which is very easy, like meaning because all the beats are submitted by the competitors, it's easy to win all of them. So in this case, if you try to go with the optimal bidding strategy, which is not a universal feasible, but is ROI feasible, you go with a pair of 1 and n, meaning that you submit a bid of 1 and you just repeat it n times, 1, 1, 1, 1. Then you will see that this bidding strategy is going to win 1 unit in competitive rounds, because I think the C is a number much greater than 1, it's not possible to win those. But in the last one, which is easy round, this bidding strategy is going to win all the n units. So that's good. So then you can calculate the V up to be almost 2 times n. Then I think if you try to go with the universal feasible policy, the optimal universal feasible policy would be 1 and 1. Right? Remember, once I choose the quantity to be 1, the B should be truthful. Truthfulness meaning that the B should be 1B1, which is equal to 1. And that one wins 1 unit in all the rounds, regardless whether competitive or not. So in the easy round, it actually doesn't win much, so it only wins 1. And because of that, if we try to calculate the ratio of what you are getting under op versus what you are getting under the universal feasible policy, that ratio would go to 2 as epsilon goes to 0. Right, so meaning that like in a bad example, you need to have like certain like round which is very easy and certain rounds that are very difficult. You can extend that idea when you have more than when you need to submit more than 1 pair. But overall, that's the kind of overall idea how to get the tight lower bound of 2. Okay, and then after we got this result of like the price of universal feasibility to be 2, we got really excited and see that can we try to see that price on the actual like data from EU ETS from the carbon market run in Europe. And sorry, the wrong thing. So we try to actually estimate this competing bid from the auction that the EU ETS auction data that EU ETS provides. And then now we look at the perspective of like one particular bidder, and for that bidder generate her valuation ID from a uniform distribution. So what you see here is the price of universal feasibility as a function of M. When I'm assuming that the competing bids are coming from the this like data that the EU ETS provides. In the worst case, when M is equal to 1, the price of universal feasibility is like 1.25. Rather than being 2. And as M increases, the price of universal feasibility is kind of converges to 1. For the typical value of M, which is kind of 4.5, so the price of universal feasibility is 1.05, which is good, meaning that the cost of universal feasibility is like 5% in typical scenario. I'm just making sure that the bidder satisfied their ROI constraint all the time by following this bidding strategy. But the cost that they pay at the end of the day for it, regardless of like the number of auction, and in this like a practical setting, would be kind of at most 5%. Yes.
You might have mentioned this, but I missed it. So the values in the simulation are assumed to be IID from 0, 1.
Yes. And then we also normalize the competing bid submitted by others as well.
Okay, so the bid data is only used for the competing.
Yeah, exactly. Yeah. Yes.
What is the ROI?
How we set the parameter ROI? I think we must have set the gamma to be 0. But then we also try to change it, but which is not mentioned.
I have a follow-up question. So I understand ROI is well motivated in the context of online networks. Is it well motivated in this context that I think of an auction that there is this kind of ROI constraint?
Yeah, good question. I think classical mechanism design look at like quasi-linear maximization for traditional reasons. But I think that given we thought about like a different behavior for the bidders, and in practice, I don't know, maybe it is like more investigation, but at least given the empirical statistics that bidding are bidders are usually like useful rather than doing demand reduction, perhaps in the better model compared to fight. Thank you. Okay, so now like how good the UF policies are. So I think they're pretty good. The loss is upper bounded by factor of 2, and in the like real world inspired settings, the loss is even like much smaller. The cost would be like less than 5%. Okay, let's try to answer the third question, which is it easy to learn the optimal UF? Because we still need to learn the Qs, right? So even we have this nice nested structure, I still need to learn the quantities. So let's try to see how we can learn these optimal universal feasible policies over time. And then related to what, like, for example, Doris was talking about in this like online setting. So it's kind of a repeated setting. Bidders submit bids, they observe feedback, they update their bidding strategy, and this cycle will continue. And we want to make sure that over time, as they're going through that cycle, they end up like converging to the optimal queues. Okay, so, and then as a reminder, learning the optimal UF policy, we know that is equivalent to learning queues. Then we have these like key lemmas that actually enables many of the results in this paper. And this key lemma tells us that the optimal queues is coming from this optimization problem. These key lemmas try to relate the value that the bidder gets from a one M uniform bid to the value you would get from M1 uniform. And here is just try like to show that without not going to the details. So it tells you that this optimal queue is coming from that optimization problems. And then it turns out that optimization problem is a set function optimization, where this set function is submodular and monotone. And then after you have that, there are existing polynomial time algorithm that gives you 1 minus 1 over the approximation. So then my job would be kind of quite easy for that part of the paper. And I have like a recent paper that tried to kind of design online learning algorithm for monotone submodular function, but there are also like earlier work. So, but the results is more general that the submodular is solving online submodular maximization, just kind of one of the side product of that. Nonetheless, for the full information setting, you get sublinear regret of square root t, and for the bandit setting, you get the regret in the order of t to the power of. Okay, so then the last question was that is it easy to learn the optimal UF policies? Yes, it's easy. You can still like learn the optimal queues over it. So let me try to wrap up. Maybe look at the bidding problem in uniform price auction, because we noticed that the theoretical results says something, empirical results says something else. We wanted to bridge the gap between these findings in the literature. And to do that, we look at value maximizing bidders in uniform price auction, which is motivated by online ad market works that people have done in the auto bidding regime. Then we introduced the idea of the universal feasibility, meaning that we wanted to make sure that the bids submitted by these bidders are always feasible, they satisfy the ROI constraint. And then we characterize the optimal universal feasible policy. We show that it's almost truthful, it has this very nice necessary structure. We also characterize the price of universal feasibility. We show that it's upper bounded by 2. In practical setting is even much better than this factor. We also try to learn these optimal UF policies over time, and we show that this can be learned polynomially over time using existing algorithms. So future research direction, we want to like go beyond uniform price auction. For example, look at this for pay-as-bid auctions, which is also another type of auction format that is being used in practice. By the way, my PhD student Rigel is here that might go in that area because he has his poster presentation on pay-as-bid auction, and not for value maximizer, for utility maximizer. And then also, we want to also consider generalized value maximizer for both ROI and budget constraints. So yes, thank you so much for listening. This is a link to the paper, and that's my email. I would be happy to take any question you